Everybody. My name is Angela Jensvold, and today we're going to talk about two-dimensional kinematics, and we're also going to talk about this year's exam format. First, let's go over the homework I gave you last week. It says a ball is kicked from the ground. Let's just draw a picture. Kicked from the ground at initial speed v0 at an angle theta above the horizontal. Find the magnitudes of the velocity and acceleration of the ball when it reaches the highest point. Okay, so we know that the horizontal component of the initial velocity is v0 cosine theta, right? And then if we trace the path of this object at the peak, it's only going to be moving horizontally, and the horizontal velocity doesn't change. So that's still going to be v0 cosine theta. And then the vertical velocity is non-existent. It's not moving up or down at the peak. And then in terms of the acceleration is just downward with a magnitude of g. But since we're asking for magnitudes, we don't really care about direction right now. So the velocity at the peak is going to be v0 cosine theta. And the acceleration of the peak, remember, it's just magnitude, is g. Okay, I hope you guys got that. Okay, so today we are going to look at learning objectives, change to B, C, and D. These are learning objectives. Those are in the course and exam description. So they are derive an expression for the vector, position, velocity, or acceleration. So if we go back to the one we just did, the vector velocity would be, remember we were just doing magnitude, but if we convert it into a vector, it would be v0 cosine theta I, and the acceleration would be negative g j, okay? Just to give you an idea of what the vector velocity and vector acceleration would be. Calculate kinematic quantities of an object like displacement, velocity, acceleration, and then describe, I'm circling this, I think it's especially important this year, motion of an object in 2 dimensions in terms of the consistency between position, velocity, and acceleration. So why do I think describe is so important? Well, I hope everyone saw the announcement on Friday. First of all, you guys are first, right? So you are the first AP exam on May 11th. So if you're in Hawaii, you're going to have sunrise physics. I can't think of a better way to start the day. What else? There's going to be 2 questions. So one of them will be 25 minutes long, and then you'll have 5 minutes to upload that, and then you're done with question 1. You can't go back to question 1. Then question 2 is going to be 15 minutes, and you'll have 5 minutes to upload that. Okay, so the question 1 is 60% of your grade, and question 2 is 40% of your grade. Just want to make sure you saw the types of questions. So this column here is question 1, and this column here is question 2. This is a publicly available document on the College Board website. I think it's AP COVID-19 updates at collegeboard.org. I think if you Google it, you'll find it. So the first question assesses your ability to do these 4 things: analyze representations, determine scientific questions, analyze data that are in graphs, and develop an explanation. Okay, and then in terms of question 1, this is the longer one, and it says it has an increased emphasis on analyzing concepts. Okay, and it says less emphasis on pure calculations. Okay, so that's good to know. And then question 2 says it's going to be basically an experimental design. You're going to have to use graphical analysis, and you're going to have to find, discuss experimental uncertainty. And those have been asked in the past. So, but we'll look at one of those today, one of those experimental design questions. Okay, but I looked at this bullet list, and because I've been using the course and exam description all year, and I noticed these 4 bullets are science practices. This is science practice 1, this is science practice 2, this is science practice 4, and this is science practice 7. So I just want to draw your attention to those. Hopefully you've been practicing these skills all year, so it's not really a problem. But science practice 1, I'm just going to highlight one example. Describe a relationship between different types of representations of the same situation. So a representation could be a force diagram, a graph, an equation, a narrative statement. You should be able to go back and forth between those of the same physical situation. Make a claim. We're going to make a claim today. We're going to practice that. Linearize data. We're going to do that today. And support a claim from evidence. We're going to do that today because we're going to make a claim and then we're going to support it using the data that we were given in the problem. Okay, so that's what I'm going to try to emphasize. You know, not exclusively, but I'll try to practice these types of questions in our lessons together. So let's get started. This is a representation. This is a graph. It's just a sketch. It's not a plot, just a sketch of a graph. And I want you to describe the acceleration of the object, and I'm going to give you 30 seconds. Okay, so let's see how you did. Now you will be able to use a keyboard for your exam, so you should be able to type it. So let's practice that. So what should we say? The horizontal acceleration starts at 0, then increases and is positive. It's not an English test, so this is because the slope starts off at 0 and increases. How about that? Okay, what about the vertical? The vertical acceleration is constant and negative because the slope is constant and negative. Right? Okay, so we just did physics by typing. It's great. This question is from AP Classroom, from AP Physics C Mechanics, AP Classroom. Okay, so let's get rid of that. Do another one. Okay, now we're going to make a claim. Okay, I'm going to give you a little bit longer for this one. I'll just give you 1 minute. Might not be enough time, but see how far you can get. Okay, so another comment that was on that the public webpage was that a calculator is not required for the exam. It said that a 4-function calculator could be useful. A 4-function calculator just means add, subtract, multiply, divide. Okay, so that's something good to know. I mean, a lot of the problems on the Physics C exam have been in terms of variables, which I know students maybe dislike, but looks like that will continue this year. So can we do this question without a calculator? Well, okay, horizontal and vertical acceleration. acceleration is change in velocity yet. So first we need to figure out what's going on with velocity. So velocity, let's say in the x direction, is the displacement in the x direction, the rate of change of displacement in the x direction, right? Okay, so why don't we get the displacement, the horizontal displacement for each time period? Let's see if we can do it without a calculator. We might mess up a little bit, but. So the change there is 1.1. Oh, that's ugly. Let's try that again. 1.1. The change here is 0.9. Change 1, 1.1, 1, 0.9, 0.9, 1, and 1.1. We did that without a calculator. We don't need it. Okay, now let's do the vertical displacements. This is 1, 1.5, 1, negative 0.4. That's not 1, that's 0. I told you I was going to make a mistake, and that's not 1.5, it's 0.5. Oh, geez, negative 1. Maybe we do need a calculator. Maybe that's why they're telling us to use that 4-function calculator, so you don't make the mistakes that I'm doing. What is this? Negative 1.6, negative 2, negative 2.5, negative 3.5. I'm sure I made some mistakes in there. I'm just trying to get a general idea. Okay, so that is, so the time intervals for all of those calculations we made are the same. So we can say that the horizontal velocity is proportional to the horizontal displacement, and the vertical velocity is proportional to the vertical displacement, okay? Because the time intervals are the same. All right, we want to know acceleration. Well, acceleration in the x is change in x velocity over time. But again, the time intervals between the change in velocities will be the same. So I'm going to say acceleration in the x is proportional to change in the x velocity. Okay, that's really the change in the displacements between two successive time periods. Now I'm just going to look over here. I guess I could calculate them. So you might even be able to just look and see, like, I look at this horizontal position and I see like the change is almost all the same. So I feel like the displacements are almost the same, which to me says the velocity is pretty much constant and acceleration might be 0. But I know you might be uncomfortable for you not to calculate it. So this would be negative 0.2, 0.1, 0.1, minus 0.1, minus 0.1, 0, 0.1, and 0.1. Now look at those numbers. They're hovering around 0, right? And they fluctuate a little bit. Any data is going to have experimental uncertainty. But I'm going to make a claim right now and say acceleration in the x direction is 0. That's my first claim. Now I need to make a claim about the vertical. This is all over the place, so I can kind of see already that the acceleration isn't going to be 0, but I'll calculate it because I think you guys might be uncomfortable if I just eyeball it. So negative 0.5, negative 0.4. What is that? Negative 0.6, negative 0.6, negative 0.4, negative 0.5, and negative 1. It's kind of all over the place. What my claim is going to be is that acceleration in the y is non-zero, okay? Those numbers that I just calculated are not hovering around 0. So my claim is that the acceleration is 0 in the x and acceleration in the y is non-zero. Okay, based on my calculations of the displacements and how much those displacements are changing. Okay, take a shot at these ones. These objects start off with the same speed. Okay, so why don't we compare the air times first, the time that these two objects are airborne. So we know that distance equals rate times time. Whenever you use distance equals rate times time, that rate has to be an average speed, okay? So the time is the vertical displacement divided by the average speed in the y direction, okay? So what did I just do? No, it's okay, okay. All right, so delta y, they both have the same vertical displacement, but their average velocities are different. Which one of these is going to have a higher average velocity in the y direction? A is. A will. So that means the time for A is smaller than the time for B. Okay? Basically, you look at this equation, you say, if the average velocity for A is up, the time for A is smaller. Okay? All right, let's erase all that, and then we'll compare their speeds, their impact speeds. Okay? So we'll use one of the kinematic equations. Let's do object B first. We know that object V, the horizontal velocity is constant. So when it hits the ground, it's going to have a speed V naught, a horizontal component of its speed is V naught, right? Because it was thrown horizontally at a speed of V naught, that doesn't change. Now in the vertical direction, let's use this equation. I'm going to call down positive, okay? So down is the positive direction. All right, so V naught y for object B is 0, right? Because it's launched horizontally, so this is 0. So Vy, the final vertical velocity, is equal to the square root of 2g delta y, okay? So then in order to get the, let's see, impact speed, speed means magnitude, right? So we want to do square root of Vx squared plus Vy squared. So we would say square root of Vx is V naught and Vy is 2g delta y. That's Vy squared. Okay, so that's for object B. Now we need to do object A. Okay, for A, the x is easy. It's always 0. So all we have to do is look at the y. So Vy final is equal to V squared is equal to V naught y squared plus 2g delta y. Okay, so it's V naught y is really just V naught because they were both launched at a speed. Well, let's call it V naught. Okay, so Vy, the final speed when it hits the ground, is square root of V naught y squared plus 2g delta y. Oh my gosh, look at that. Their impact speeds are the same. Okay, very nice. Okay, describe the acceleration vector at the peak. 30 seconds. Okay, so should we type it? Describe the acceleration vector. The acceleration vector points downward with magnitude g. How about that? I hope you guys got that. I only gave you 30 seconds because I think that one was pretty easy. This one too, I'm going to give you 30 seconds. Okay. So we're really trying to make sure you know this. The magnitudes of the accelerations are equal to each other and equal to g. It's just talking about magnitude, right? There's no acceleration in the horizontal direction for a projectile, and the only acceleration is in the vertical because the Earth is pulling down on the object. I always lose my cursor. Okay. Oh, I wanted to get rid of that. Okay, so now you have another one. Try to type it. See if you could type it. 30 seconds. Okay, so, oops, I don't know what I did there. The text box, okay. So what are the vertical components of velocity and acceleration? Okay, so I'm going to say Vx is VH. Horizontal component of velocity doesn't change, right? So it's just this, it's just the original, which they called VH. Do we usually use a capital V for velocity? No, but to avoid using a subscript, I'm making a big V and a regular X. You just need to make sure a physics teacher can understand what you mean when you type this stuff. Okay, Vy is, at the peak. Vy is 0, right, guys? Because at the top, it's not moving up or down at the peak. Okay, and then acceleration in the X is 0. Not accelerating in the X. Ay is this magnitude? Let's just put negative g. Okay, so what are the vertical and horizontal components of the velocity and acceleration at the peak? So we were able to type it out, even though it's not what we're used to doing. It can be done. We can use a capital acceleration for A. Usually that's area, but could have, in the context of this problem, can a physics teacher understand what you mean? I think so. Okay, this is, remember you guys have to comment on experimental uncertainty. Here's your opportunity. Okay, so let's think about this. You're taking a ping pong ball and you're dropping it, and the measured time you got is higher than your calculated. Well, what equation did you use to calculate it? Probably this one here, right? You're releasing it from rest, so the V naught T term is 0. So if you solve for, time. Okay, let's solve for time. Time would be the square root of 2y over g, right? Okay, so in this experiment, Where do you think the biggest source of uncertainty is? Is it in the height that you measured when you dropped the ping pong ball? Is it the human reaction time of operating the stopwatch? Or could there be something else? Well, let's look at the equation you used when you calculated it. It's this kinematic equation. What is that equation? When is that equation applicable? All the time? No, only when acceleration is constant. Is the acceleration constant for a ping pong ball when you drop it? No, I don't think so. It's so light and it has quite a high cross-sectional area. I think air resistance will have a non-negligible effect. So this ping pong ball, even if it doesn't reach terminal velocity in the time that you drop it, its acceleration is not going to be constant. What will happen to the acceleration? Maybe we'll think about that later, since we're not talking about forces, but just try to think about it maybe tonight. What would happen to the acceleration of a ping pong ball from the moment you let go and throughout the time that it descends? It's not really our topic today, but I hope you'll think about it. Okay, try this one. We've got an airplane problem. 1 minute. Okay, so this is an oldie but a goodie. You have an airplane and it's traveling horizontally, and you let one object go. I'll call this object 1. And later on, when the plane has moved horizontally, you're going to let a second object go. So what I'm drawing here is a sketch of time when we start our timer. So object 1 will be moving downward, and it will have fallen a distance. I'm going to call it y0. Okay, and object 2, I'm going to call this y. Oh gosh, I don't even know how I did that. I didn't know I could do that. Okay, so the horizontal line I drew, we're going to call that y equals 0, and we're going to call down positive. Let me put a little marker over here. Down is positive. Okay, so let's do it in red, I guess. Let's express the vertical position of object 1. So for that one, it would be y, that's the amount that it has dropped. Down is positive. So y equals, it's not the amount it has dropped, it's vertical position measured from the horizontal line of 0. y0 plus v0 y t plus 1/2 gt squared. The last term is positive because we're calling down positive. Okay, so that'll give you the vertical position of object 1 at any time. Now let's do object 2. Object 2, y0 is 0, v0 is 0, so all you have is 1/2 gt squared. Now what we're going to do is we're going to subtract these two equations because we want to know how far apart are they as time goes on. So we take the difference between the amount that they've fallen, their vertical positions basically, and we get y0 plus v0 yt, and then 1/2 gt squared minus 1/2 gt squared goes away. And now we have an expression for the vertical gap between the two objects. What happens to that gap as time goes on? As time increases, the value of that equation is going to increase. So the vertical distance between the two objects increases. Okay? I think you should have, I recommend having a pen and paper. If you're going to type in your answers, have a pen and paper so you can draw sketches and stuff, and then you can type in your answer when you're done solving it. Okay, find the horizontal and vertical speeds and acceleration at Q. 1 minute. Okay, so you want to get the horizontal and vertical speeds at Q. So let's just draw the components to begin with. This one would be V naught cosine theta, and this vertical would be V naught sine theta. Okay, now remember in the horizontal direction, the speed doesn't change, so I'm going to draw that over here. It's the same, V naught cosine theta, and this whole thing is symmetric, so it will have a downward component of V naught sine theta. Now, we don't care that it's downward because the question is asking us about speed, but just to make our diagram nice. And then the acceleration is just g, and they're just asking for speed, so we don't care that it's down. But okay, so horizontal speed is V naught cosine theta. Vertical speed is, remember, it's speed. I know it's down, but we're not going to put the negative, V naught sine theta. And then AX is 0, AY is g. It's the speed, so we just leave off the negative. All right, so we know that the second question is going to be experimental design, right? So I found an experimental design question from 2018, and it's on kinematics. It's on one-dimensional kinematics, but that's the closest I could find. So I figured you guys would rather practice just get exposure to the kind of skills that you're going to be assessed on question 2. Okay, so you've got an electromagnet, there's a metal sphere. The electromagnet turns off, and that's when the timer should start, and the timer stops when it hits that pad. Problem is, oh, and they're trying to find G, by the way. That's the whole point of this experiment. Problem is, in part A, the student notices that the electromagnet releases the sphere after the timer begins. So the timer starts and the electromagnet doesn't release the sphere. It releases it after you start your timer. Would the value of G be greater than, less than, or equal to the actual value? Well, we're coming back to our same old trusty equation, right? Because V naught is 0 because it's released from rest. Or it should be H, right? They're calling this H. So I guess I'll erase it. Okay, so H is 1/2 GT squared, right? They're looking for time. They're calculating time, and then they're measuring it. So let's solve for that. 2H over G square rooted. Okay, so oh no, they're looking for G. Sorry. Okay, I'm not erasing that. G is 2H over T squared. This is the one we want to look at because they're trying to find G. All right, and what happened was the timer releases the sphere after. Okay, so the timer started before the sphere was released. That means that your time is going to be longer. Your measurement of time is going to be longer. And this is an inverse square relationship. That means G will be smaller. So I'm going to say less than. And my justification will be that the measured time is longer. the measured time is longer, and there's an inverse square relationship between G and time, so G will be smaller, okay? So those are the kinds of experimental uncertainty questions that are usually asked in Physics C. Okay, now they fix the electromagnet, they fix the timer, everything's good. And what they're gonna do is they're gonna vary H, and they're gonna measure the corresponding times and graph it to get G. Okay, so what quantity should be graphed to yield a straight line whose slope could be used to calculate G? Well, we just had this equation, 1/2 gt squared, right? And we know that for a line, y equals mx plus b. Well, we don't have a vertical intercept today, okay? So our y variable is going to be h. Our x variable, we need it to be t squared. And then our slope will be 1/2 g. So slope is 1/2 g. So in the vertical axis, you should graph h, and on the horizontal axis, you should graph delta t squared, the interval of time squared. Oh, so that's why they gave us these extra rows. Okay, so delta t squared in seconds squared, okay? And we can fill it in using a 4-function calculator, 0.011. All you need to do is multiply, right? It would be 0.105 times 0.105, 0.045, 0.117, 0.161, 0.203. Okay, so those are the times. Now it's going to ask us to graph. Okay, so when you graph, you have to label your axes and get a nice scale that uses at least half the grid. Okay, if I make the width of the first box 0.05, the width of the next box also has to be 0.05. Okay, and then I'm going to plot the data just kind of sloppy in the interest of time. I'll just, oh, that's not even right. Okay. Why isn't it? Okay. Oh, so messy. Oh my gosh. Okay, the data points are pretty ugly, but all right. So we have our data points. Now I'm going to do a best fit line. The goal is to get the same number of points above and below. It's not amazing. It's not amazing. I don't even know if I can move this thing. Okay, we're just going to use it. We're just going to use it. Otherwise, we're going to run out of time trying to make a perfect line. It doesn't. The main idea is to get the concept of how to use this line. Okay, it's going to ask us to use the line to get G. Do you remember in the last slide we said the slope is 1/2 G? So we need to find the slope of this line. In order to find the slope of this line, you take 2 points on the line. So it's possible you could be given a graph on this year's AP exam, and then you have to use the slope to find something. It's a very common thing that's asked on the AP exam. So let's find the slope of this line. You do not use data points. You never use data points to get the slope. We're gonna, do you see how I circled 2 red points there? Those aren't data. Okay, so the slope is, okay, I'm just eyeballing this, okay, because it's just, I don't even know, 0.95. I know that's wrong, but 0.15, I know that's wrong. 0.19 minus 0.02. The denominator is right. Okay, so slope, remember slope is 1/2 g. So 1/2 g is equal to, what is that, 0.8 over 0.17. I don't know what that is, but when I did this earlier using a better line, I got 4.57. So I'm putting a squiggle there. That means like approximately equal to, but not really. I'm just doing this in the interest of time. Okay, so 4.57 meters per second squared. Okay. That's half g. So then what is g? G would be twice that, 9.1 meters per second squared. Okay, so I think you get the idea. You don't use data, you use points that are on the line to calculate the slope. And usually from the slope, you find a physical quantity, but it's not always the slope. It might be the intercept. It could be any part of a graph that you're asked to be used. So I'm not saying that it's always going to be the slope. Okay. Okay, then it says, right, like I said, calculate an experimental value for G. Okay, now another student in the data finds the table. Should we try typing this one? The student's equation for the distance is, they gave you that. Derive an expression for velocity. Can we do this while typing? Derive? Let's give it a shot. Okay, so what we're going to do is say V equals dx dt. And so we're going to differentiate. Oh, I should have said y, honestly, right? Because it is a vertical motion. Okay, so let's take the derivative. Let's differentiate. So it'd be 2at plus b, right? Should we plug the numbers in? We can. What is that? 2a is 11.5. I'm just going to say 11.5. T and b is negative 0.524. Okay, so we just derived, while typing, an expression for the velocity of the sphere. Great. Calculate the new experimental value for g. So for that one, there's two different ways. We know that v equals v naught plus, well, it would be, yeah, plus at, right? So g is the coefficient of the t term. Therefore, g is 11.5 meters per second squared. Okay, we just did it. We calculated using, maybe we used in our head, we doubled the number. Oh no, we didn't have to. We had to double the number in our head a moment ago, but you can also use a paper and pencil and just double, what was that? 5.75. You can do that, or with your 4-function calculator. Okay, using 9.81, calculate the percent error. I challenge you to type it. So it's 11.5, the experimental, minus, can I make an absolute value symbol on here? Wow, so impressive. 11.5 minus 9.8 absolute value over 9.8. Well, I guess I should have taken the absolute value of the whole thing. I was impressed with myself too early. I'm just going to leave it, you guys. I'm just going to leave it. You get it. Can a physics teacher understand what I'm writing? Yes, and that's all that matters. So 0.172, I think I got earlier, and multiply that by 100 to get the percent is 17.2%. Okay, we did this. We did this question by typing. Assuming the sphere is at a height of, okay, this will be a little bit more ugly. I have to be honest, but I think we can do it. Okay, so you know v squared equals v naught squared plus 2g, I'll just put y. It's really delta y, but I'm going to put y. Okay, so v is, we're going to do a square root. So I'm gonna have to square root this whole thing. V naught squared. What is V naught? Let's go back to our original expression. V naught is the coefficient of the t term, so it'd be negative 0.524, right? So negative 0.524 squared plus 2 times g. What is our g? 11.5, right? So can I just do 23? Because 2 times 11.5 is 23, right? I think so, yeah. Times delta y. So that would be y final. You know what I should? I feel like I want to go back up here. I don't want to leave that as y. Y final minus y initial. I feel better now. Because it really wasn't y, it was delta y. And we can get around putting in a delta by doing y final minus y initial. It's fine. We just need to practice this and we'll get better and better. Okay, so y final is 1.4. And if you look at the equation, there's a constant of 0.08, which is your y naught, 0.08. Now I have to put my final bracket on, and then I have to raise it to the 1/2 power. If you put that in your calculator, you're 5.54 meters per second. Okay, so, you know, okay, they're going to give you better numbers, so you could do it on a 4-function calculator. But I feel like we were able to do a pretty good job on this, typing out, you know, we did a derive, we did a calculate, and the last one, yeah, you couldn't do 0.524 squared on your calculator, but they're probably not going to give you constants like this if they know, you know, you're having to type it. So I thought that was pretty good. I think we can do this. Okay. Okay, so just to review, your first question is 25 minutes, focusing on those 4 science practice I talked about. It's more qualitative, no calculator required. The second one is 15 minutes. It's going to be an experimental design, so you're probably going to have to do graphical analysis, identify experimental error, and that's 40% of your grade. In terms of projectile motion, make sure you separate out the horizontal and the vertical, solve for the unknowns in x, solve for the unknowns in y. Time is the same for both directions, so use that information to bridge the gap between the two. I'm going to leave you this question, which is a review of relative velocity that we did last time when we were together. So take a screenshot, do it for homework, and thanks for watching. Tomorrow, Mr. Frensley will be back doing forces, and stay home, everybody.